We will not go to Mars, not you, not me, not our children, and probably not even their great-grandchildren. I know, it may be a bit painful to hear, especially when we see Elon Musk promising colonies on Mars by 2050, when NASA is planning manned missions in the 2030s, when people sell us the dream of a multi-planetary humanity, and especially when they show us images of SpaceX with shiny rockets launching into the infinite and beyond. But the problem is, that dream is exactly a dream. A dream, and today I will explain to you why, point by point, with science, with data, with the harsh reality of physics. So pay attention. I'm not saying this to discourage you, quite the opposite. I think that by understanding things realistically, it's quite simple. It will allow us to perhaps point to something more important, but before going further, let's ask a simple question. What makes a planet habitable? The answer seems basic. The fact that it is inhabited. Let me explain. If a planet has never had life, then perhaps it simply cannot. It's a bit like an empty restaurant. Either it just opened, or the food is terrible. And in the case of Mars, the restaurant has been open for 4 billion years. So this logic seems a bit circular, but it holds a profound truth. Habitability is not just about having water and the right temperature. It's about having a stable, complex system that can sustain life for billions of years, and that is much rarer than we think. So let's start from the beginning. Was there ever life on Mars? And if so, what does that teach us about the chance of returning there? Just a few weeks ago, in September 2025, NASA made an announcement that shook the world. The Perseverance rover discovered something intriguing in Jezero Crater. A rock sample they call Sapphire Canyon, taken from a rock nicknamed Shiava Falls. Before explaining why this is important, let me set the context. Jezero Crater is an ancient lake. 3.5 billion years ago, water flowed into it. We know that because we can still see traces of a fossil delta. Sediments deposited in layers, just like in a lake on Earth. Perseverance is rolling on what was once the bottom of a lake on Mars. Imagine that scene for a second. You're driving a 1-ton robot on what was perhaps billions of years ago, the shore of an alien lake. This rock at Yavafol has strange patterns, colored spots. These spots are arranged in a leopard pattern, and within those spots are 2 special minerals, vivianite and greigite. Why is this important? Yes, because on Earth, these minerals often form when bacteria use chemical reactions to produce energy. In other words, it's like they found traces of a bacterial meal billions of years old. Vivianite is a hydrated iron mineral. On Earth, it is found in sediments, in peat bogs, around decomposing organic matter. Greigite is an iron sulfide that some bacteria on Earth produce directly inside their cells. But pay attention, and this is where it gets interesting. Similar minerals can also form without life. They are just ordinary chemical reactions, high temperature, acidic conditions, or simply the passage of time with the right chemical ingredients. Actually, that's the fundamental problem of astrobiology. How can we distinguish signs of life from ordinary geological processes? How can we be sure we found traces of life, and not just complex chemistry? Scientists use the so-called cold scale for the reliability of life detection. Basically, it's a scale from 1 to 7, measuring the level of certainty we can have when finding traces of life. Level 1, we've detected something interesting. Level 4, we have multiple converging clues. Level 7, we have absolute proof of life. And right now, with Shiava Falls, we're at about 2 or 3, so it's interesting but not conclusive. For context, the Martian meteorites found on Earth with presumed traces of life have been stuck at level 2 for decades. So why so cautious? Because the history of astrobiology is full of false alarms. In 1996, NASA once announced finding traces of life in a Martian meteorite. 28 years later, the scientific consensus is that it was probably just geology. But let's go back extremely far into the past. More than 3 billion years ago, during the so-called Noachian period, the name comes from Noachis Terra, a region on Mars covered with ancient impact craters. At that time, Mars was different. There was liquid water on the surface, a thicker atmosphere, rivers, and possibly U2K, where Perseverance found those famous spots, that is an ancient riverbed. That is the Neretva Vallis, 400 meters wide. But how do we know? Well, thanks to orbital missions, Mars Reconnaissance Orbiter, Mars Express, Mars Odyssey. These probes have mapped the planet with incredible precision, and everywhere we see traces of water, valleys carved by rivers, plains where rivers emptied into lakes, minerals that only form in the presence of liquid, clays, sulfates, carbonates. The whole geology tells the story of a wet planet. Imagine flowing water, carving the landscape, depositing sediment, lakes filling up. They dried up with seasonal rhythms, possibly even oceans in the northern plains, and exactly the kind of environment where scientists think life could have emerged. But there's a big problem. Even in its best conditions, Mars is not Earth, far from it. The problem is that many people imagine Mars was once a bit like primordial Earth, lush green, full of life, and it just failed. Well, that's wrong, completely wrong. And it's important to understand, even at its peak, Mars was a harsh world. Why? Well, for several reasons. First, distance from the Sun. Mars receives only 43% of the solar energy that Earth receives. Even with a thicker atmosphere, temperatures were cold. We're talking about average temperatures around 0 degrees Celsius in the best case, compared to 15 degrees Celsius on Earth today. Next, gravity. 38% of Earth's. This may seem trivial, but it changes everything. Weak gravity. That means the atmosphere escapes more easily. That means different geological processes. That means life as we know it would be very unlikely to survive there as it is. And above all, it's like that. Mars has been losing its atmosphere. The process had already begun, and the planet was doomed from the start. Jean-Pierre Bibring, a French expert on Mars who directed the Omega instrument on the Mars Express probe. He dedicated his entire career to studying the mineralogy of Mars. In fact, I was able to interview him on this channel. I'll leave the link in the description. Anyway, compared to Mars, his conclusion is undeniable. Omega. It's a spectrometer that analyzes the chemical composition of the Martian surface from orbit. Pixel by pixel, it mapped the entire planet, and what it found is that Mars's geological history is recorded in its rocks, according to Bibring. Mars went through 3 major periods. The first was the Pholocian period, where water was abundant and clays formed. Then came the Thakian period, where water became acidic and sulfates formed. And finally, the Siderian period, where water disappeared and gave way to the oxidation of iron. This evolution took place in just a few 100 million years. That's extremely fast on a geological scale, and it shows that Mars was never truly stable for long. So, what can we hope existed on Mars? And Bibring is clear. At best, bacteria. At the bottom of a puddle, for an extremely limited time, no forests on Mars, no animals, no plants. Only bacteria that perhaps survived a few million years in harsh conditions. And that's the extremely optimistic scenario. Because even if life could exist on Mars, it would have to face an environment that was deteriorating extremely rapidly. Imagine bacteria thriving in a lake that gradually dries up. The atmosphere gets thinner, radiation increases, temperatures drop, and after a few million years, nothing is left. And if there really was life on Mars, that's what it would have looked like. And that tells us something important for today, because if Mars couldn't sustain life naturally, with all its initial advantages, that is, water, atmosphere, geothermal energy, how could it artificially sustain human life? Because just look what happened afterwards. Look what Mars became. About 4 billion years ago, Mars underwent a catastrophe. It lost its magnetic field. To understand the magnitude of this catastrophe, we first need to understand what a planetary magnetic field is on Earth, on ours. The magnetic field is generated by the dynamo of our core, iron. This rotating liquid iron creates a gigantic electromagnetic field that covers the entire Earth. This field is like our invisible shield. It deflects charged particles from the solar wind and protects our atmosphere from space erosion. Without it, Earth could be like Mars. And do you know what protects Earth from this space radiation? The invisible shield that surrounds our planet. Mars lost it. And when a planet loses its magnetic field, it loses everything. So why did Mars lose its magnetic field? Simply because it is smaller than Earth. Thus its core cooled faster. The dynamo stopped working, and with it the magnetic protection. Without protection, Mars's atmosphere was literally blown away into space by the solar wind, like opening all the windows of a house during a storm. The MAVEN and Mars Express missions have confirmed. This erosion still continues today. Every second, Mars loses about 100 grams of atmosphere to space. It sounds small, but over billions of years, it's equivalent to an entire atmospheric ocean disappearing. The problem is that this is irreversible, completely irreversible. So what does Mars look like now? We will systematically inventory its atmosphere, 0.6% of Earth's pressure. To give you a concrete idea, it's like being at an altitude of 35 kilometers. At that altitude on Earth, your blood actually boils, you can't breathe, and liquid water cannot exist on the surface. Its composition, 95.3, 2% CO2, 2.7% nitrogen, 1.6% argon, and only 0.13% oxygen, making it toxic to say the least. And even if you have an oxygen mask, the pressure is so low that your lungs cannot function properly. Average temperature minus 80 degrees Celsius, with peaks of minus 125 degrees Celsius at the poles in winter. And even summer on Mars, at best reaches 20 degrees Celsius, but only at the equator at noon and only on the surface. As soon as the sun sets, the temperature drops sharply. So why such extreme fluctuations? Because the atmosphere is too thin to retain heat. On Earth, our thick atmosphere acts like a blanket. On Mars, it's like sleeping outside on a midwinter night. And what about radiation? Oh, without a thick atmosphere and without a magnetic field, the surface of Mars receives a lethal dose of radiation 100 times that of Earth. Over 4 billion years, the entire surface has been sterilized, and considering this has lasted 4 billion years, it is almost certain that the entire planet has been completely sterilized. To give you an idea, an astronaut on Mars would receive a radiation dose in 1 year, equivalent to what a nuclear worker receives in 20 years on Earth. That's a dose that significantly increases cancer risk, and worst of all, it's not over yet. The Martian soil itself is also toxic. It contains perchlorates, which are chemical compounds, but they are found at concentrations 1,000,000 times higher than on Earth. These substances are lethal to most life forms on Earth, perchlorates. So what exactly are they? Oh, they are salts of perchloric acid. On Earth, they are used as explosives, rocket fuel, or super strong herbicides. Just imagine. Try growing tomatoes in soil soaked in bleach mixed with gunpowder. That's roughly the idea. Try growing seeds on Mars. Why so many perchlorates? That's due to billions of years of oxidation by UV radiation, with no atmosphere to filter the sun's rays. The Martian surface has been bombarded by this radiation, turning normal minerals into toxic compounds. Even if we could clean the soil, there would still be a lack of something essential, nitrogen, an element indispensable for all complex life. On Earth, it makes up 78% of our atmosphere. On Mars, there is almost none. Nitrogen does not exist in a usable form. Nitrogen is the foundation of proteins, DNA, and all complex organic compounds. Without available nitrogen, life cannot exist. And on Mars, nitrogen is either trapped in the extremely thin atmosphere or locked away in inaccessible minerals. But most importantly, what is missing is an ecosystem. On Earth, everything is connected: the water, carbon, and nitrogen cycles. Plants produce oxygen, animals exhale CO2. Bacteria recycle nutrients, oceans regulate climate, and forests influence rainfall. It is a system of extraordinary complexity, with millions of interacting species and delicate balances maintained over many years on Earth. Positive and negative feedback loops help stabilize the whole. On Mars, there is nothing. No water cycle. Water exists mainly as ice at the poles and in the ground. No carbon cycle. Furthermore, there is not enough atmosphere to sustain significant exchanges, and there is no life to maintain balance. It's like trying to run a car with no engine, no fuel, and no wheels. Even if we fix one element, others are still missing. And on Mars, it's not just one or two things missing, but the entire system. And then, there are dust storms on Mars. They can last for months and cover the entire planet. In 2018, a global storm lasted nearly 3 months. It covered the planet with a thick layer of dust, so that the solar-powered Opportunity rover did not receive enough light to operate. So, it died right there in that storm. And this dust is everywhere. It gets into every mechanism. It is electrostatic, so it sticks to everything. It's abrasive, like ultrafine sandpaper, imagine. Try maintaining complex equipment in an environment where everything is regularly covered in corrosive dust for months, imagine. Try farming when the sun disappears for a quarter of a year. That's the reality. Mars is not a pristine land just waiting to be awakened. It is a world fundamentally hostile to life as we know it. Every aspect of the Martian environment is a deadly challenge. The atmosphere, the soil, the temperature, the radiation, the lack of an ecosystem all conspire against life, and that is not temporary. It is not a bad phase to get through. That is the permanent state of Mars for 4 billion years, and it will continue for billions more. But I anticipated some comments. Maybe you'll say that we have technology, that we can overcome any obstacle with a bit of perseverance, right? That we can create protected habitats, pressurized areas, life support systems. So let's look specifically at what that would require. Start with the journey. To get to Mars, you have to wait for the right launch window. This happens about once every 26 months. You have to wait for the orbits of Earth and Mars to align optimally. Why this constraint? Because the planets actually move. Earth orbits the Sun in 365 days, Mars in 687 days. In 687 days, you therefore need to wait for the two planets to be in the right configuration to minimize distance and required energy. Miss your window and you'll have to wait another 2 years. Imagine logistics applications. Imagine a technical problem delaying your mission by a few weeks, and then you're 2 years behind. Then the trip lasts from 6 to 9 months. A trip in cramped space, with limited supplies, and especially being constantly bombarded by cosmic radiation. By the way, let's talk about radiation. In space, far from Earth's magnetic field protection, astronauts are exposed to galactic cosmic radiation and solar flares. These high-energy particles penetrate. The spacecraft walls are as if they don't exist. Some studies estimate that a trip to Mars could have a mortality rate of 50% to 150%. Would you board a plane with a 1/2 chance of crashing? Where does this number come from? It comes from the cumulative effects of radiation, microgravity, psychological isolation, and technical risks. Each day in space increases the risk of cancer, cardiovascular issues, immune system decline over the months of travel. The effects of microgravity also need to be addressed. It is a medical nightmare. In microgravity, the human body deteriorates rapidly. Bones lose 1% to 2% of mass each month. Muscles atrophy. The cardiovascular system declines. Vision deteriorates. Why? Because our bodies are designed to adapt to Earth's gravity. Mechanical constraints to remain robust. Muscles need to work against weight to stay strong. The heart needs to pump against gravity to remain efficient. After 9 months, your astronauts arrive in poor physical condition. They have lost 20% of their bone mass. Their muscles are atrophied. Their immune systems are weakened. Now they must face the environment, one of the harshest in the solar system. Throughout the trip, they need to recycle air, recycle water, and manage waste. Technically, we know how to do it on the International Space Station, but over a few months, not years, air recycling is very complex. It is necessary to remove CO2, regenerate oxygen, filter contaminants, and current systems have a 95% recycling rate. It sounds good, but over 9 months, this 5% loss accumulates. Water recycling is even more critical. On the ISS, we recycle urine, sweat, air humidity, but there is also loss there. And on Mars, you cannot carry water from Earth. Then there is food. 9 months of travel, plus time on Mars, plus the return trip. We are talking about 2 to 3 years of food for several people. That's tons of food to carry. But anyway, let's assume they arrive alive. Now, they need to land. And this is one of the biggest problems with the atmosphere. The Martian atmosphere is technically too thin to allow effective braking by parachute like on Earth, but it is too thick to ignore entirely like on the Moon. On Earth, the thick atmosphere allows effective braking by parachute. On the Moon, there is no atmosphere, so only retro rockets can be used. Mars is the worst of both worlds. Its atmosphere is only 1% the density of Earth's, so it creates friction and heat during descent, but not enough to brake effectively, resulting in landing on Mars being perhaps one of the most complex engineering challenges in space. Look at the solutions used to land the Curiosity rover. NASA had to invent a sky crane. A retro rocket system lowers the rover with a cable, and it works for 900 kilograms. But for a human mission, it requires tens of tons of equipment. SpaceX proposes landing with retro rockets, similar to the moon. But the problem is, it consumes a lot of fuel. And the fuel must be brought from Earth or produced directly on Mars. And in both cases, it's a huge engineering challenge. Let's talk about producing fuel on Mars. That's called ISRU, in situ resource utilization. The idea is to use Martian resources to produce everything needed for fuel. The idea is to produce methane and oxygen from the Martian atmosphere and groundwater. CO2 from the atmosphere plus water yields methane plus oxygen. Chemically, that's feasible. But look at the numbers. Because to launch a rocket the size of Starship from Mars, you need about 1,200 tons of fuel. 1,200 tons. The Perseverance rover carries a small experiment called MOXIE, which produces oxygen from the Martian atmosphere, and in 2 years, it has produced 122 grams of oxygen for 1,200 tons of fuel. You need thousands of such machines operating for years, and that, of course, assumes we have the necessary energy, because these chemical processes consume a lot of electricity. And where does this energy come from? From solar panels, because, as we recall, on Mars the sunlight is only half as intense as on Earth, and dust storms can last months. So what about nuclear? Well, you'd need to bring a reactor from Earth, with all the associated risks. Okay, let's assume we landed successfully. Now we need to survive. First need, oxygen. A person consumes about 550 grams of oxygen per day. For a 6-person crew over 2 years, you need more than 2 tons of oxygen, so you need the ability to produce, store, and purify it. Second need, water. Yes, there is water on Mars, but in the form of ice. So you need to find, extract, and purify it. And that with equipment that must operate at -80 degrees Celsius in a corrosive environment with frequent dust storms. Mining ice on Mars is a bit like plumbing, in a freezer with spacesuits and tools that can break at any time. Third need, food. And that's an absolute nightmare. Growing food on Mars is a bit like trying to garden, but in a freezer filled with bleach under UV lights. No breathable air, toxic soil. You need to clean and enrich it, add all the missing nutrients, which means import soil from Earth or artificially create a nutrient substrate. Temperature. Well, you need constant heating with all the energy problems that entails. Martian greenhouses will need constant heating to maintain a livable temperature. Atmosphere. Well, you need to create pressurized, airtight greenhouses that can withstand dust storms and radiation, and maintain an atmospheric composition compatible with plant life. Yes, as we said, on Mars the light is half as intense as on Earth, so that means must compensate with artificial light. And once again, that consumes energy and therefore requires more energy. And even if we solve all these problems, what do we produce? A few vegetables, but certainly not enough to feed a colony. No animal protein, no food diversity, just enough to survive, nutritionally speaking. A human needs over 40 essential nutrients, vitamins, minerals, amino acids, fatty acids. An unbalanced diet, even temporarily, can have serious consequences. But on Mars, for example, how do you produce vitamin B12? It only exists in animal products or certain special bacteria. How do you produce omega-3? How to ensure adequate supply of calcium, iron, or zinc? And then there's the psychological aspect. Eating is not just nutrition, but also pleasure, culture, and social connection. Imagine having to eat for years only greenhouse-grown vegetables. No variety, no flavor. So the result, any colony on Mars will be completely dependent on supplies from Earth, food, medicine, spare parts, complex equipment. Most everything will come from Earth. But remember, we can only send cargo every 26 months. A technical problem, a breakdown, a delay, and it's a disaster. Imagine a critical part fails, like the air recycling system. On Earth, you order a part. It arrives the next day. On Mars, you have to wait for the next launch, maybe 2 years later. And calling that colonization is self-deception. It's more like assisted survival, like saying we have colonized Antarctica. There, we only maintain scientific bases that must be continuously supplied from outside. And here, we haven't even mentioned the long-term effects on human health. The gravity on Mars, let me remind you, it's only 38% of Earth's. How could that affect our development? Currently, we don't know, and no human has ever lived long enough in microgravity. To be clear, can children develop? In reduced gravity, can women carry a pregnancy to term? Can the cardiovascular system adapt? Currently, we have no idea. There are also unknown risks. The impact of Martian dust on lungs, consequences of living in a closed artificial environment, the interaction of all these stress factors. So here is the verdict. Even with major technological advances, establishing an autonomous colony on Mars will require decades, even centuries of development. And we're talking about keeping a few dozen people alive, not creating a civilization, no economic development, no building cities, just keeping a few humans alive in harsh conditions with continuous technological support and total dependence on Earth. But you will say, what if we terraform Mars? And what if we terraform the entire planet to make it habitable? And what if we recreate the atmosphere, climate, and ecosystem? I warn you from the start, we are entering the realm of pure science fiction. And I will explain why terraforming is the ultimate idea, the dreamy idea. Instead of adapting humans to Mars, what if we adapt Mars to humans? We transform the atmosphere, climate, environment, and recreate Earth-like conditions. Imagine blue oceans on Mars, white clouds, green grass, a breathable sky, a planet where you can walk in a t-shirt and breathe freely. And that seems reasonable, because if Mars was once habitable, why can't we bring it back to that state? Why can't we just reverse the process that made it barren? Well, because that is physically impossible, and I will explain it to you point by point. In 2018, a NASA team, this team, led by Bruce Jakowski, published a study that shook the scientific community. Their conclusion: Mars simply does not have enough CO2 to create a significant greenhouse effect. So let me explain. To terraform Mars, we need to thicken its atmosphere, create a greenhouse effect to warm the planet. And to do that, we need CO2. How much? Well, we need an atmospheric pressure similar to Earth's, about 1,000 millibars. Mars currently has only 6 millibars, so in reality, we need to multiply that by 160. What does that specifically mean? Well, we need about 1,000 times more CO2 than what is currently in Mars's atmosphere. It's like trying to fill a swimming pool with a cup of water. And where do we find all this CO2? Scientists have inventoried all possible sources on Mars. The polar ice caps, because that is the most obvious source. Mars has water ice and frozen CO2 ice caps at the poles. If we vaporize all of it, we get 1.2% of Earth's pressure. 1.2%, not even enough to start the greenhouse effect. And moreover, that's if we vaporize all the polar ice with what? Well, it would require enormous energy to sublimate billions of tons of ice. What about CO2 in the ground? Well, by heating all of Mars's regolith, we could release CO2 absorbed on dust particles. Maximum result, 4% of the required pressure. 4%, and to do that, we would need to heat the entire surface of Mars. Several meters deep, imagine the energy needed to heat an entire continent. And carbonate mineral deposits. Mars contains carbonates, minerals that store CO2, but in negligible quantities, less than 5% of the required pressure. And to extract them, we would need to mine the entire planet to a depth of 30 meters across the entire surface of Mars. It's like trying to dig the Suez Canal on every square kilometer of this planet. Faced with that reality, some propose even more extreme solutions. Redirect comets and asteroids to Mars to bring water and CO2 from outside. Jakowski's calculations show we need thousands of comets, thousands, and how can we redirect them? With what technology? With what energy? And why not manufacture artificial greenhouse gases, such as chlorofluorocarbons, more effective than CO2? So it's possible. In theory, but it would require enormous chemical plants operating for centuries, with resources that must be imported from Earth. And even if we could, these gases are unstable. They decompose under UV radiation, so they need constant replacement. But suppose we miraculously find all the CO2. There is still another more fundamental problem. Mars continues to lose its atmosphere because it has no magnetic field to protect it. Any atmosphere we could restore would gradually be eroded by the solar wind. That is exactly what happened 4 billion years ago. To prevent this erosion, the planet's magnetic field would have to be regenerated, and that is even more impossible. Earth's magnetic field is generated by a dynamo in our core. Rotating liquid iron creates a huge electromagnetic field. This dynamo, it operates thanks to heat from the core, supplied by natural radioactivity and residual heat from the planet's formation. To recreate that on Mars, the dynamo in its core would have to be restarted. In other words, it would need to be heated and its motion restored. The energy required at the planet's center is then completely astronomical. We are talking about a geological process that takes 1 million years. It would require the equivalent of the energy produced by the sun in a few years. Focus on the core of Mars. And how to do it? Well, no idea. No technology, however conceivable, can achieve that, and even beyond imagination, even with perfect technology that doesn't exist. And that would take years and centuries, because Earth's formation was a process that took an extremely long time. Look at Earth's history. It took billions of years for it to transform from an uninhabitable sphere into the Earth we know today. To change a planet's atmosphere, to modify its climate, and create stable ecosystems, technology is needed. Perfect. And it would take a time that, in any case, is incompatible with human projects. And the biggest problem is that we don't even know how to create an ecosystem. And in fact, that was attempted in the 90s. The Biosphere 2 project tried to create a closed ecosystem in Arizona. On Earth, with access to all resources and technology, the project was still ambitious, recreating multiple ecosystems on land, rainforest, ocean, desert, savanna, all within a closed structure of 3 hectares. 8 people were to live there for 2 years in complete self-sufficiency. Result, complete failure. Oxygen dropped from 21% to 14% in 16 months. The residents suffered from altitude sickness. They were exhausted and unable to work effectively. Why did this oxygen drop occur? Because super-rich soil was brought in to promote plant growth. These soils nurtured a lot of bacteria and fungi, which consumed oxygen. When they released CO2, the trees and shrubs were too young and too few to compensate. Pollinators disappeared, possibly due to an explosion of the predatory ant population or because the glass blocked UV rays. Because bees see in the UV spectrum to find flowers, the water system became contaminated, biodiversity collapsed, and the ecological balance was broken. And that happened on Earth under ideal conditions with regular access to external resources in emergencies. David Tillman, one of the ecologists who evaluated the Biosphere 2 experiment, made a fairly simple calculation. If we extrapolate the cost of Biosphere 2 to a space colony, it would cost $85,000 per person per month without guaranteeing survival, and all that just to maintain a minimal artificial environment. Its conclusion: trying to replace it is extremely costly. The services that Earth's ecosystem provides free of charge to humanity, that is the cost of sustaining a few people in a closed environment. Imagine the cost of terraforming a pristine planet. And here's the harsh truth. Terraforming Mars is pure science fiction. The laws of physics, chemistry, and biology make this project impossible with any conceivable technology. Not difficult, not expensive, simply impossible. Mars will never be a second Earth, never. And it's important to understand that because this illusion sometimes leads us away from what's essential. Very often we forget something fundamental. We are not independent entities that can survive anywhere. We are intrinsically linked to the planet Earth. Every cell in our bodies, every physiological mechanism of ours, all are adapted to Earth's environment. Unfortunately, we are not space explorers. We are Earth explorers. Literally, our technology, at least current technology, can help us survive temporarily in harsh conditions, what space missions and submarines face, but that cannot allow us to escape our natural environment. And this is where it gets interesting, because when we understand why Mars is impossible, we understand something fundamental. First, we must learn to preserve our own planet before we attempt to terraform other worlds. Because honestly, if we have already failed to maintain Earth's habitability, a planet perfectly suited to our needs, then how can we create habitability elsewhere? How can we claim to build a house when we cannot even maintain the house we live in? Can we really think we can create a garden on Mars when we are struggling to maintain the forests on Earth? I'm not saying it will never be feasible, but the logic is undeniable. Mastering Earth's ecosystems is an indispensable prerequisite for any terraforming effort, and currently we are still quite far. When we understand that, we also understand that, contrary to what is often heard, there is not necessarily an opposition between ecology and space exploration. Studying Mars helps us understand Earth better. By studying how Mars lost its atmosphere, we better understand how to protect our own atmosphere. By studying the greenhouse effect on Venus, we better understand how climate change affects life on Earth. Space exploration develops technologies useful for protecting our environment. Observation satellites, recycling systems, renewable energy, all benefit Earth. Research on closed ecosystems allows us to better optimize resources on Earth. It also enables the development of more efficient agriculture and higher performance recycling systems. More sustainable cities. The goal of this video is not to be the final conclusion on the issue, but the idea is that space exploration should not be a means to run away forward. On the contrary, it should be a means to better understand how we should protect our planet. And in a way, instead of being sad, I see something beautiful in this realization, in the entire known universe. Earth is and remains unique. This small blue sphere, lost in the vast universe, is currently the only place we are certain life exists, and that, perhaps it is worth taking the time to reflect on this idea. Among billions of planets in our galaxy, among billions of galaxies in the observable universe, currently we know of only one planet with life, just one, and finally. Perhaps the real question is not how we should go to Mars, but instead how we should keep the Earth habitable, and that is perhaps the greatest challenge awaiting us.